So good morning and welcome to lecture 5. Since you told me that you didn't do measure theory in your mathematics courses so far, we'll have a short interlude on that today, and tomorrow we'll also look at Lebesgue integrals. We do this for two reasons. So we'll have a short recap of basic notions of measure theory without proofs. That has two reasons. First of all, we spend too much time on it if I provide all the proofs, and the proofs are not that difficult, and hence they will go to a problem sheet. The central proofs will go to the problem sheet, but that will be good practice. Short recap of the basic notions without proofs for two reasons. The chief reason from the abstract point of view is that the spectral theorem for self-adjoint operators we're going to prove in the next few lectures requires, as we already saw from the axioms of quantum mechanics, the notion of projection-valued measures. Projection-valued, and the projection-valued is just a small modification. Projection-valued measures, and unless we know what a measure is and what a Borel measure is, we're lost there, and I rather explain it than to refer you to the literature, because that can be quite intimidating if you start in the wrong point. And the second thing is that the most commonly emerging infinite dimensional separable Hilbert space. Now you say, hang on, isn't there up to unitary equivalence only one such? Yes, there is, but then separable. But then it depends on how you represent it in order to make good use of it in physics. The most commonly emerging infinite dimensional separable Hilbert space in quantum mechanics is the Hilbert space L2 on some Rd, often d equals 3. And informally speaking, but it's not entirely correct, this is these are all square integrable functions on Rd. Well, not quite, because you have to take equivalence classes of all square integrable functions, because if two square integrable functions are the same almost everywhere, what does that mean? Well, we'll see. Then they belong to the same equivalence class, and then they're counted as the same element of this. That's the first thing. And the second thing, if I say square integrable, it is not square integrable with respect to the Riemann integral, but with respect to the Lebesgue integral. And that makes all the difference. You probably did in mathematics for physicists a number of theorems telling you under what circumstances you can exchange integrals and limits, or integrals and sums and so on. And you know that if you use the Riemann integral, you have rather strong conditions like uniform convergence and stuff like this. Well, the Lebesgue integral heals this. The Lebesgue integral is a very proper notion of an integral, which for Riemann integrable functions agrees with them, but which no longer poses such strong conditions, from the point of view of Lebesgue theory, virtually none, on the functions in order to be able to exchange limits and integrals. So that is what the physicists say for reasonably well-behaved functions. Well, you no longer even need to say this. You say for these and those functions without this rather uninsightful qualification of being reasonably behaved. So the Lebesgue integral is the physicist's integral. But it's also the mathematician's integral, because this space equipped with its inner product, blah, 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 is only complete if you use the Lebesgue integral. It wouldn't work with the Riemann integral, okay? It simply won't. It's not a Hilbert space then, okay? So there is no way in quantum mechanics to avoid the Lebesgue integral. Everything else is child's play, okay? So we're going to do that, and what we do today is the preparation for that. So we start with section 1, general measure spaces. Now, the first definition we provide is that of a measurable space, also called a sigma algebra, and it looks a little like the definition of a topology, but it's different. So the basic definition is, so let M be a set, well, a non-empty set. Then a collection of subsets then a collection of, could I have more quiet, please? Please. Then a collection of subsets small sigma, so that's a subset of the power set of M. The power set of M contains all the subsets. Then a collection of subsets sigma Pm is called a sigma algebra for M. Now this is very cryptic, a very cryptic piece of terminology, a sigma algebra for M, but that's the traditional term. If, so not any collection qualifies, like for a topology, not any collection of subsets qualifies as a topology. Here, the first requirement is that the entire set M also be part of the collection. The second requirement is that if a set A is part of this collection, then its complement with respect to the set M also be part of the collection. So if a set is contained, its complement is contained, very simple. And the third requirement is that if you have a sequence, an infinite or a finite sequence, it doesn't matter, A1, A2, dot, 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 they all lie in sigma. That's the first condition. And they are pairwise disjunct. So AI intersection with AJ is the empty set for I not equal to J. Then the union over all these is again an element of the collection of the sigma algebra. So any such choice of subsets, like in a topology, there are three conditions they need to satisfy in order to not be called a topology, because they're different conditions, in order to be called a sigma algebra. So that's the key notion. Now, we'll see what one can do with the sigma algebra and why one needs one for certain purposes. And I will, however, first introduce some terminology that already hints at that and which one should keep in mind. So terminology. So if you have an A in sigma, is called a measurable set. It's called a measurable subset in M. Okay? So the whole thing we're going to do is we want to be able to assign, and now I use a colloquial term, volumes to subsets. And naively, one might think, well, you take a subset of an M, so they say M is R to the 3, or R2 or something. Why wouldn't we be able to assign a meaningful volume measure to any subset? Well, it turns out that's not meaningfully possible with all the conditions you have on that. A volume will be called a measure soon, right? It's just an example. And it turns out you need to select a subset of all Yeah, a subset of all possible subsets. Only the sets in a sigma algebra can be meaningfully assigned a volume, a numerical number for the volume, 7 liters. Okay, so that's what's going to happen. So that will be the purpose of this. So the sigma algebra could be called, instead of sigma algebra, which is rather cryptic, it could be called the set of all measurable subsets. Okay, why you need these conditions, we'll see. And the pair M with a choice of measurable subsets, M sigma, M with a choice of sigma algebra, is called a measurable, and now I use color, a measurable space. So we already have a double working of the word measurable. You can have a measurable set, it's an element in sigma, and that pair is then called a measurable space. Okay? Why I write this measurable here in red is because already in this headline I had general measure spaces, not general measurable spaces. Well, I'm not responsible for the terminology, so don't shoot me. I'm just pointing it out. We'll soon define what a measure space is. A measure space will be a measurable space plus a measure, which is a map that assigns to each measurable set a number, which then will be the volume of that set. Okay, I'm just pointing it out. Don't shoot me. Okay, so this pair is called a measurable space. So a remark, clearly taking sigma to be the entire power set. So it's a little like the discrete topology. Choosing the discrete topology, if you choose all subsets, they satisfy the conditions of a topology, but choosing all subsets also satisfies the requirements of a sigma algebra, is a sigma algebra. In general, however, and that's a remark you're going to expand on the problem sheet, in general, however, it does not provide a useful sigma algebra, a little like the discrete topology doesn't provide a useful topology, right? It is one, but it's not particularly useful. A useful sigma algebra if M is non-countable. So for countable sets, that means in converse, for countable sets, that's very often a meaningful idea to do that. But as soon as the sets are non-countable, which is the case for any complex vector space, well, it contains non-countably many elements, then that choice becomes rather problematic and useless. Okay, but anyway, that's just a remark. So because you might say, couldn't I just consider every set a measurable set? Because it still satisfies this. Yes, but it's not meaningfully so. We will come to that. Okay, so look for an example on the problem sheet, and you may also want to read up on Banach-Tarski paradoxon, which uses the axiom of choice and is often presented as something, or historically as something that should cast doubt on the axiom of choice in set theory, because by the axiom of choice you can construct a subset of, say, R2 or R3 that is not measurable in a meaningful sense. Well, anyway, what one can look at, if you take the axiom of choice, you can say the Banach-Tarski paradoxon tells you, for instance, for R to the 3 or wherever you want to look at it, that you rather pick a sigma algebra that's less than this. Okay? So that's all justifying that one doesn't simply do the naive thing and chooses or tries to establish all sets as measurable sets. Okay, so fine. This is a definition, and we breathe life into it by the following definition. A measure a measure mu from sigma to r. Well, I think we want r plus 0. A measure is a, hang on, yes, is a map on a measurable space, M sigma, is a map satisfying two conditions. Condition 1 is that the empty set, which is always measurable, because if the entire set is in there and its complement, that means the empty set is there. The empty set gets measure 0. Okay, that's very, very reasonable. I'm sorry, I don't know why I wrote this here. I'm sorry, well, it's true what's written here, but it's an unnecessary restriction. I was getting ahead of myself. So here in the definition, it is, of course, because of this union. I could have written the disjoint union, that's true, but it's not false, but it's totally unnecessary to require this. So if you have elements in the sigma algebra, then the union is in the sigma algebra. If they have no intersection, well, nothing goes double in the union, but of course that would be eliminated by the union in the first place, okay? So I'm sorry, this qualification was not necessary. I was getting ahead of myself because that's obviously something you need now here. If you now have a sequence, which could be a finite or an infinite sequence, A1, A2, and so on, that is in sigma, and that's pairwise disjunct. So AI intersected AJ is the empty set for all I non-J. Then the measure of the union of those, so we know that the union of such sets, if they are measurable, that the union is measurable. That's axiom 3 of the measurable sets. So we can even write this, because you see the mu only eats measurable sets, only elements of the sigma algebra. So we have measurable sets, the M can eat this, and then this is equal to, well, equal to the sum, all n greater or equal to 1, of the measures of the individual sets. And if they were not pairwise disjunct, then of course here you had a double counting that is eliminated here by the union. So hence here we need this pairwise disjunct condition. And this property is often called sigma additivity, but it's rather reasonable. Could call it a reasonable condition, right? So that's a measure, and so you see the whole raison d'être for a measurable space is that on it I can assign to each measurable set an actual number. You could call it the volume of that set. And that you can do in many ways. Now you might say, well, maybe isn't there an obvious volume? Well, not quite. For instance, in probability theory you do this a lot, and there you may assign to a set, which is a collection of events in probability theory, you could assign the probability or the probability density on the set and so on. Okay, so it needn't be the physical volume, if you wish, and well, in mathematics there's no physical volume in the first place. Okay, so this is a rather general notion, but on RD we'll have a canonical measure, the Lebesgue measure, but we're coming to that. But we start in this abstraction in order to be sufficiently prepared for all the applications of measure theory we'll find during the course. And well, it's a rather intuitive subject, and the style is essentially like topology. So all of you know the definition of a topological space and continuous maps and so on, yeah? Okay. Well, if not, you can ask me during the problem class tomorrow. Okay. So we have the terminology. The triple of a measurable space, measurable space together with a measure. This together is called a measure space. So measurable is just this part, and the measure space is the triple. Okay, so probably that's the reason why people call this is sigma algebra instead of the set of measurable sets, because there are so many measurables around. Okay, but I think even without the terminology, you get the idea. You equip a measurable space with a measure. Okay. So now, I mean, so far nothing happened. I mean, we only had theorems. Okay, so we didn't leave out any proofs. Now we have some properties. Properties of a measure. Okay. So the first property I would like to mention is the monotony. Monotony. The monotony of the measure means that if you look at a set A1 that lies inside a set A2, and both of these, of course, are supposed to be measurable, okay, then it follows that the measure of the set that is a subset of the other is less or equal than the measure of the superset. Okay? Don't be fooled. If this is a proper inclusion, it still could have an equal sign here, because there could be just one point missing and the measure won't see it. Well, that's informal speaking. They could differ only by a so-called set of measure zero. We'll come to that. So don't draw false conclusions from this. Then there is a property of the measure that's called subadditivity. Well, this is just a property. What happens if you drop the pairwise disjunct condition? So if you say, okay, you have a sequence of, you have some sequence of measurable sets. If that is the case, but you do not know whether they're mutually disjoint, well, then you still know that the mu of the union of those, which is still guaranteed to be a measurable set, according to the third axiom, you can only conclude that it's less or equal than n equals greater equal to 1 of the measure of the an, roughly speaking, because on this right-hand side, you may overcount quite a bit, because whenever two sets have a non-empty intersection, of course, that is not showing up in the union, because the union will identify the points, right? But it will show up over here. But so if you can't ensure this, then you will greatly over-measure the volume on the right-hand side. Hence, you get this estimate. However, very often, you're only interested in the estimate, so that's a meaningful generalization.
You have a question about the sets. Because they are all countable, aren't they?
Who?
The sets of the Rns you define.
The sets, the AN, it's so one AN, A7 is...
The AN set is countable.
I said it's a sequence.
It's a sequence. Okay.
It's a sequence, yes, countable, yes, that's the whole idea.
Okay,
Yes, no. So that whenever I give numbers A1, A2, A3, very obviously this is only a countable collection. That's why I call it a sequence. Okay? Yes. No. This is intentional. This is not. Well, I'm trying to avoid child's play. So if this was.
Important.
Pardon me?
But
it is important. Yes, of course.
Yeah.
Yes, it is important. Hence, it's defined that way. So 3. Okay. So we have something that we call convergence from above, from below. So assume you have a sequence, you have an increasing exhaustive sequence of measurable sets. That's a very important construction tool. So what is that? That is A1 is contained in N2, is contained in A3, and so on. So you have an increasing, exhausting sequence. That's the increasing bit. And the exhaustive bit, so increasing is this, and exhaustive is that indeed if you take all of them together, you recover the entire space. Okay? That's the exhaustive thing. No, not the entire space, I'm sorry. You get a set A, right? So you get a set A. Then, if you take the limit n to infinity of the measure of the ANs, then you can pull the limit in, so to speak. You get the mu of the A. Okay? Well, the limit of n to infinity is kind of meant in this way, hence we write it like this. So this is the continuity, in quotation marks, and convergence, continuity, I'm sorry. Continuity. Now, because you can pull a limit in, so it's continuity from below. Okay? And there's also a continuity from above. Which works with the intersection, but there's an extra condition. Yes, well, that's right. Well, if you it depends on your perspective. You're right. If you start with this, you say you get a set. If you change perspective and you say you have a set, which is very often in practice the case, so your remark is correct. But if you start with a set, you might wish to find a sequence that goes to this set because you might want to start on the right-hand side and write it as the left-hand side. And then you need the condition that, I could have, instead of writing this cloud and making it a condition, you're right, it's not a proper condition. It's more like a notation of what this A in here means.
So you would write down an increasing exhaustive sequence to the set A or something.
To the set A, something like this. Yeah, exactly. And you could also say an increasing sequence, and then you write the union into here. That's exactly right. It's just I chose this version, which I agree may be a little misleading there, because very often you start with a set, and then you want to find such a sequence to start from the right-hand side, and then it's more meaningful to talk about it like this. Okay. So in a similar vein, we have yes.
Does A have to be measurable?
Well, it would automatically be, because the A's are a sequence of measurable sets. So then, according to the last axiom, it is measurable. Yes. Yes, and if you start here, very obviously, because otherwise you couldn't feed it into the mu. So again, if you start from there, you say you want a measurable set and so on. Okay? Okay. So then you have the continuity from below. Continuity from below. So that would now be a decreasing from above. You're very unforgiving today. Okay. So continuity from above. So you have a decreasing sequence that's enveloping a set. So that's, again, the same remarks apply as to where you start and so on. So you start with A1 being a superset of A2 being a superset and so on. They're all supposed to be measurable sets, okay, of course. If you want for notation or depending on your perspective on which side of the equation you start, you want that if you take the intersection of them all, you get A. Now you could more meaningfully ask the question, well, if these are measurable, is the intersection measurable too? And, because the axiom only talks about the at most countable unions, right? You get the at most countable intersections too, that will be on the problem sheet by using the Morgan's rule. So I just remarked this is in sigma due to the Morgan rule. Well, rule is actually a theorem, and actually this comes from set theory. So the fact, so you know that, right? It's if you make an exclusion jump a union, well, in our case like this, then that is the intersection, the sign flips, that's the intersection of all the complements. Or the other way around, the complement of an intersection is the union of all the complements. Okay? And that is, at the end of the day, this comes from the axioms of set theory, how you define the unions and so on, and how unions are defined is in fact an axiom of set theory. It's not as trivial as one might think from kindergarten. Okay, so so if you have something like this, and that's the important bit, otherwise I could have said similarly for decreasing series, and there is a condition, and the condition is that the highest set here, the biggest superset, that has finite measure. I should have probably, I said the mu goes to r plus 0, is that right? Yes. I shouldn't have said that. So if you go back to that, the mu should go from sigma to r bar plus 0. And the r bar, so it's first r bar, and we'll look at the r bar soon, but the r bar is r union with minus infinity and plus infinity. Okay, so we invent 2 points called minus and plus infinity. Then you say, well, that's silly. Didn't we learn in school we shouldn't do that? And rather, if something takes infinite values somewhere, we should rather take that point where it takes infinite values out of the domain, right? Isn't that what you do with 1 over x, the function 1 over x? You define it on R without the 0 in order so it doesn't take infinite value. Well, that's the alternative to that. You say, no, I want to keep my domains untouched, in this case what the sigma algebras are, what the sigma algebra is, what a measurable set is, but I allow for the value infinity. Okay? We'll see this in another place as well, not only for the measure, but also for measurable functions, measurable maps, which we haven't defined yet. But you can already imagine, if you have a definition a little bit like a topology, and there you have continuous maps, you will certainly have maps that preserve that structure, right? So those will be the measurable maps. We'll come to that. Okay, anyway, so here's the condition that the superset is already finite, and then the same thing applies. You can take the limit n to infinity of all the measures an, and that's just the measure m of a, but now a is the intersection, right? So that's the continuity from above. And, well, proof problem sheet. Well, that's the first thing we have to prove anyway. So far, there was nothing else. So there's a final important definition of this section, so I squeeze it here. A measure mu is called finite. Well, some people call it sigma finite because, well, measure mu is called finite if I talk about a measure, there's always an underlying measurable space. So I do not always write this down. So a measure mu is called finite if, and now it's not for all, but if there exists a sequence A1, A2, dot, 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 dot of measurable sets, such that if you now really exhaust with the union n greater equal to 1 of the ANs really hits the entire space, such that the mu of the AN is finite for all n in n. So a measure is called finite, or sigma finite, if there exists an exhaustive sequence that now exhausts the entire space such that every single of those measures is finite. doesn't mean that if you go to sigma of m, it's finite. Okay? So there's a subtle definition here. And we'll mostly look at finite measures. And that's an important tool for proofs. Are there any questions so far? So we start with a set. We make a selection of sets of subsets which we call measurable, and in order for our theorems to work, they need to satisfy certain conditions. Basic idea is not every subset can be meaningfully be called a measurable set for our purposes. Well, once you've chosen these sets that are distinguished in this way, that constitute a sigma algebra, you may now choose on this measurable space a map mu, which actually takes each such distinguished set and assigns it a number. Okay? So far, that's it. That's it. So apart from so for a while people thought that you can really assign to each subset a measure, and that led to great trouble, right? And the breakthrough was to recognize, no, that's not possible. Not for the purpose you have in mind. I mean, of course, you can define anything, but the question is, can you then prove what you want to prove, and does it have the properties you would like to have of a measure? That's the point, right? So that's the key idea here. Simple, right? Very simple so far. And it remains simple. All is simple. Well, in teaching, you only have one choice. You can either say, oh, this is going to be very complicated, and then you hope that everybody will pay attention, or you say, this is going to be very simple. I don't know whether it depends on your character or not, or the character of the audience. I like to say it's very simple, because then you would feel embarrassed if you don't understand it, so you'll go home and secretly study up, right? Okay. So you see, psychological manipulation is present everywhere. Okay, so next section is called Borel sigma algebras. Aha, we already know sigma algebras, and if I now talk about Borel sigma algebras, apparently that's a specific type of sigma algebras constructed in a specific way. But because before we go, and they will play the main role, okay? So this was very general measure spaces so far. Now we come to Borel sigma algebras. But before I tell you what precisely a Borel sigma algebra is, we'll answer the question, how does one specify in practice a sigma algebra? Well, it's a little like in topology. You know, in topology for finite sets, you can write down a collection of subsets and you check the axioms and everything is fine. But if I ask you to write down the topology, the standard topology of RD, you cannot do this explicitly. What you do, you define these soft balls or open balls, right? And then define a subset of RD to be open if around every point there exists a soft ball that lies entirely within this set and stuff. You see, and of course all of this is very intuitive and fine, but then you have to prove that that really constitutes a topology. But if I tell you, do you have an intuitive overview over all open sets in RD, or let alone or even R or R2? Actually, the honest answer is no, not really, because they can be very strange sets, right, with very, very strange stuff, okay? And with sigma algebras, it's the same. So, of course, we have an intuitive notion of there's a subset and it's measurable, it has a volume, this one is measurable, has a volume. But there are very strange sets, or collections of such sets, and that's the point, that are measurable. Well, again, measurability is not the property of an individual set. It's a property of a collection of sets. Agree? Right, from our definition. So It's a little bit like vector space, right? I talked about this before, right? If I just write down a certain object and say, is this a vector? You need to say, well, I can't tell. I need to have the entire space, and then I know it's an element of that space, but being an element of the underlying set of that space doesn't qualify it as a vector unless the whole set has this structure with the addition. You understand? So it's you can't say, oh, this is a vector. You can only talk about vector spaces, and you can call the elements vectors. And it's a little bit like this here. You can't say, oh, how does a measurable set look like? You can only say this is a system of measurable sets, right? And if you then have such a system, then you pick one, then you call this measurable with respect to the system. And so it's okay. And then so you need to write this down concretely, and it's sometimes rather difficult to get an overview. And one way, and of course one way is you already have a measure space. We'll see that example too. And from one measure space you construct another one. That's called inheritance. You know how good that is if you're old enough, okay? So, but what if you don't have a measure space yet, and you are a measurable or a sigma algebra yet, and you want to start with one? And one very good way to do so is the following, and it comes in the form of a theorem because it contains a claim. It's a definition theorem. The smallest sigma algebra, sigma, for a set M that contains, that doesn't mean only contains, but it contains, in brackets, among other sets, other subsets of M, a collection of subsets E in the power set. And I make no further assumption on this E. I just pick a number of subsets of the big set. This one, and that one. And now I want to find the smallest sigma algebra that contains this. Is called sigma, well, quite suitably, of E. So from these E's must be in there. And what are those? Well, those are all those subsets of M. Well, if it's supposed to become a sigma algebra of M, it needs to contain subsets of M. Well, it can't contain all subsets of M, then it would be the power set. It's all those subsets of M for which it is true that, I should say the smallest sigma algebra, sigma of E, and that's Xi, sigma of E, that's its name, is called, defined as, colon, it must be true for all sigma algebras, sigma of M, that with E in them, that the A also lies in that one. Or in other words, so equal, or in other words, it's the intersection of all sigma algebras, for M, of course, that contain the set E. Okay? One can check, and that's the claim that's hidden here, one can check that this is again a sigma algebra. So prove that sigma of this E, one calls this also a generating set. I mean, that's from real life. You say, well, this set, that set, and that set, I must have measurable for my application. I must have that. which is the smallest, the most economical, if you wish, sigma algebra I can choose to have a consistent measurable space that contains those guys. What's called sigma of this set. I mean, it's really very practical. It's a generating set. E is called the generating set for the sigma algebra, sigma of E. Okay. So proof, problem sheet. That's very simple. But we have a more far-reaching result, theorem. Every sigma algebra can be written as the sigma algebra generated from some set. Well, it's not so surprising, but it's good to know that. It's almost trivial. Okay. Now, this is something you can do in practice, right? And one thing you can do, what you want to do very often, you want to link certain notions together. And this construction immediately allows to link the notions of topology and sigma algebras, or topology and sigma algebra for a set M. And that idea is the definition of a Borel sigma algebra. So you have to specify a sigma algebra, right? It's a choice. You have a set M, and you need to make a choice of a system of measurable sets, a choice of sigma algebra. Now, maybe earlier on in your problem, you already made a choice. Namely, you made a choice for a topology. Okay? So the definition is, let MO be a topological space. And the question is, you already made a choice for open sets. Couldn't you use that choice and that choice only to also define measurable sets? The answer is yes, but it's a specific way to establish a sigma algebra. Then sigma of O. So you take as the generating set all the open sets. And the sigma algebra generated by this is called, first of all, is a sigma algebra. Well, that's clear. It's called, it's clear because of this definition and the little proof. Then sigma of O is called the Borel sigma algebra of MO, right? I mean, so only a topological space can carry a Borel sigma algebra, because the whole idea of the Borel sigma algebra is that you employ the open sets in order to generate it. Okay? So you can do this. The question is whether this is a particularly good idea. Well, it turns out to be a brilliant idea. Okay? So again, why would one do this in the first place? Of course, you could take a topological space and establish a sigma algebra on it that has nothing to do whatsoever with the topology. That's perfectly fine. However, you could also have a Hilbert space with an inner product, and you could establish on your Hilbert space with your inner product a norm that has nothing to do with the inner product. You could do that, but what formulae, you will not get the Cauchy-Schwarz inequality, where on one side you have the inner product, on the other side you have the norms, because they have nothing to do with each other. So usually, if you have a strong structure that is able to imply another structure, you will establish that other structure in such a way that it's being induced. Now let's start with Hilbert space. You have an inner product, from that you induce the norm. From the norm you would induce the standard topology, by defining the soft balls using the norm. Once you have the topology, you induce the Borel sigma algebra as the Borel sigma algebra, so you only made once a choice, namely for an inner product, which is a very strong choice, right? If you made a strong choice, you usually, the weaker structures you derive from that. What you usually cannot do, you cannot come from the weaker structures and imply the stronger structures, obviously, right? Again, why would you do that? You don't have to. Well, because then you get the stronger theorems for the relation between these structures, right? So, okay, anyway, so this follows standard procedure in mathematics to induce from given structures you have already chosen, to not make yet another choice, but to induce it. Now, I point out, I did not say, very important, I did not say the sigma algebra is constituted by the open sets, because that wouldn't hold true. The properties of O, the topological axioms, are different from the axioms for a sigma algebra, right? And you could not simply choose sigma to be equal to O. That would lead to trouble in most cases, right? Unless you have the discrete topology, and then you get this all subset sigma algebra and so on. No, it is not sigma equals O. It's O is a generating system for sigma. And I'll make an example to point out that there are many non-open sets that lie in the Borel sigma algebra of a topological space. And we'll immediately make an example with the real numbers, because those will play an important role as always. You know, if you do topology, you look at the standard topology on the real numbers. And even if you look at general topological spaces, but then you make functions into the real numbers, it usually then goes at some point without saying, oh, the real numbers, they're equipped with the standard topology. And then on your topology and so on, okay? And it will be the same here. Okay, we'll come to that. So let's call this an instructive example. So let's take as the set M, let's take the real numbers. Okay. Let's take as the topology, let's take the standard topology on the real numbers. Or sometimes I call this O standard, or I call it OS. It depends on my mood, okay? So the standard topology is the, you know the standard topology, right? Defined with the, on R with the absolute value, on RD with the norm. Okay, that's the standard topology. Now, what you can do, you can look, so obviously, clearly, if sigma is defined as the one defined by all the open sets, implies, that's very simple, that an interval AB, any interval AB in R, that any interval AB, well, I could even write R bar here, because minus infinity and plus infinity is included, but we don't need this at the point, that any interval, any open interval is an element of this such constructed Borel sigma algebra. So Borel sigma algebra. Well, that's clear. So if I said it's not equal to that, but certainly it's contained, right? Because we know this contains those. But you can also look at, if you know that all the open intervals are in it, then by axiom 3 of sigma algebra, and De Morgan, so because I'm converting a union into a intersection, I know that I can take open intervals A minus 1 over n, B, for n in the integers, and I can take the intersection of any of those. So this would be my set AN. My set AN is defined like this. It's clearly measurable. It's in sigma of O. Why is it? Well, it's in sigma of O because it's an open interval. Every AN is an open interval for any n greater or equal to 1. You agree? Now I take an at most countable, according to the axiom, intersection of such. Well, it's like the union, but the complement, you go in the Morgan rule, it's the same thing. Okay? So remember, in topology, it's not the same thing. In topology, you have arbitrary unions of open sets are open, but only finite, not even countable, only finite intersections. Here you have countable unions and countable intersections of measurable sets are measurable sets. Okay? So there's no trouble here. Okay, so we do this, but we all know what this is. So if I take all these intervals, I can draw a picture. So this is the point B. Well, this is the point B, is not in the interval. This is the point A, say, and A minus 1 over n, say this is a step 1. That would be this point, but it's not in. So this is A minus 1 over n. So obviously this is the 1 on the real, is a distance 1 on the real axis. So, okay, if this is A minus this. And then the A minus 1 over n then is a half, then it's this interval, then it's a third, then it's this interval, then it's a quarter, and so on. If you take the intersection of all those, you know you will end up with the interval that contains the point A. So this is A, B. Aha! So for instance, the half-open intervals are also in the sigma algebra. Well, it's not difficult to see that also the closed intervals are in there, and many, many, many other sets. And it's so many sets, it's very difficult to really get an overview of what sets are measurable, right? But it's defined. So when you have the tools to prove it, as difficult as it may be to see or to have an idea of what all the open sets are. You have a mechanism to this well defined, right? You know what you can check it and so on, but intuition is rather difficult, or a concrete list. Okay? So this is not more abstract or less abstract than topology. I'm just mentioning this in order to warn against going home and asking, what is a measurable set? Don't ask this. You should ask, what is a measurable space? And the elements are called measurable sets. Okay. Good. And that's a very important example, these half guys here, because obviously you can take many such half-closed intervals and you get a very good idea of the real line, because you can take this one and you can cover, now I draw it a little bit like this, you can of course cover the entire real line by taking left close, right open intervals. They neatly fit together. Okay, that very often is very useful. Okay, so these in particular are interesting, and after well, I guess we need only a 7-minute break till 5 past. I'll tell you how with this idea you get the Lebesgue measure on the real numbers and on RD. Any more questions here? So let's meet at 5 past. Okay, good. Okay, so we discussed measure spaces, and we discussed how you can generate a measurable space, so a sigma algebra, from a topological space. How do you construct a concrete measure? So we only constructed the sigma algebra from the open sets. How can you construct a measure? Well, that greatly depends on the space you're looking at. And a very important notion is the Lebesgue measure, but you can't have it on any set M. In fact, it's like the standard topology. Well, you could have it on a metric space. You have it on R. You can have a Lebesgue measure. It's only for a very special type of sets. It's the RD. Okay? So if your set is M equals RD, then we can talk about the Lebesgue measure. Okay? For other sets, it's simply not there. Okay? Maybe this can be slightly generalized. There's a Lebesgue integral. It's again terminology. There's a Lebesgue integral you can define on measurable functions from any measure space to the real numbers, blah, blah, blah. But the Lebesgue measure as such is 1 on RD. Okay. So this is a special construction of a measure. And you wouldn't be surprised that it's, well, that's already said, it's on RD for some D. And it is on the sigma algebra that's generated by the standard topology on RD. But the question is, what is this measure? Then the map lambda. Now we call it a measure mu, but because this is a very special construction, the mu deserves a new name. I could write mu Lebesgue. Well, let's do that. Mu Lebesgue RD and so on. But this will be generally called lambda. And sometimes if you wish to emphasize that you're on RD rather than R, you also write lambda up D, but it doesn't mean the measure to the dth power. It's just the name for the measure. Okay. Anyway, this map that goes from sigma O into somewhere here, defined by, well, what does it need to do? It needs to take defined by, it's already defined by taking the open intervals. Now we have to need more space. Defined by, I take those subsets of RD that can be written half open interval A1, B1, Cartesian product with half open interval A2, B2, Cartesian product dot dot dot, D, many Cartesian products to AD, BD. It's not difficult to see how that looks like. In R2, this would be an A, every AI less or equal less than B, BI, equal is bad. Well, yeah. Well, could be equal as an empty set. You don't know what I'm going to write.
It could be equal, but then it's
empty. Yeah, it's empty. Anyway, I'm not finished yet. So after I wrote here, we can discuss. It's obviously something like this, right? It's a box in RD, and always the lower limit, the lower one is included. Okay, so it's sets like this, defined by, if already you fix it here, and this is now just B1 minus A1 times dot 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 times BD minus AD. So you take the naive kindergarten volume of just saying this distance times this distance and so on, where by distance you mean the real number, that's the difference between the two endpoints. Okay? So the method is the unique map, and that's the point. And that's surprising that this is the unique map. Well, it could be that there are many measures which on this set yield this kindergarten volume, but somehow globally on all the other sets in here, right? I mean, these are only very specific, it's only very specific sets in here. So obviously, they generate the whole sigma O as well. But anyway, you fix it on these special sets, and there's a theorem, and that we're not going to prove, and rather the existence and the uniqueness of this measure. This is some more work. Okay, so this is not a minor result. It won't go to the problem sheet. Also not to the exam. Okay, so but the point is there is a unique such measure, okay, that does what you expect it to do. Now there isn't, so this blah blah blah, blah is called, and hence it deserves the name the Lebesgue measure. On RD. Okay? So a remark. So if you only start with R, with the set R, and the addition on it, and the multiplication, and an absolute value. So you take the field R with an absolute value, then from this, obviously, you can construct the standard topology. From this, you can construct the Borel sigma algebra. And you can also, from alone this guy here, remarkably, you can construct the Lebesgue measure. So if you know R like you know it in, when is that, 10th grade or something, okay? If you know R like this, then you already have a full measure space. You have R with the with this Borel sigma algebra and the Lebesgue measure. Okay, so recover this in this case, and obviously on RD you then need a D here, and you need an absolute value, and then exactly the same applies. Okay, so this just shows that what you always thought is the volume of simple subsets of RD. This is all recovered by these constructions. As much as in topology, choosing the standard topology on RD, you recover the high school notions or the undergraduate notions of continuity, for instance, and convergence. Okay, so these, we start very general and then we go more and more specific, and the specificity here lies in this being the Borel sigma algebra, and in this being the Lebesgue measure. Now, if we're not on some RD, then you could still make the Borel sigma, construct the Borel sigma algebra if you know a topology for the space, and so on. Okay, and we'll have opportunity to use both. But from now on, we'll have the tacit agreement. There's the tacit agreement. Well, by spelling it out that it's a tacit agreement, it no longer is. But anyway, from now on, we have the tacit agreement that RD always be equipped if the need arises. With the Borel sigma algebra sigma of ORD standard and the Lebesgue measure. Okay? And the need arises exactly if you, in some definition or some statement, you had to assume that there is some Borel sigma algebra and or some measure. Okay. And final remark, two remarks. One, well, obviously, and that I can really say, that's not to be proven really, it's obvious. Obviously, lambda is a finite measure. So please check that. And the second is an alternative characterization. Well, unique characterization, that's the whole point. Unique characterization of the Lebesgue measure is that it is the measure that is invariant under translations of the measurable sets, under translation, so that means lambda of a measurable set A to whose every point you add a V according to the addition on RD, to the component-wise addition. So you have a set, and you shift the whole set by D. That's my short notation for that. Okay, so this contains elements in RD. You know how to do that. So that this is the same as lambda of A for all A in the sigma algebra and for all V in RD. And which sends the unit cube 0, 1 to the dth Cartesian power to +1. So that's another unique characterization of the Lebesgue measure. Okay. So fourth section is measurable maps. That's something new. Measurable maps. So again, standard philosophy. I explained this already last time, I believe. The standard philosophy is study spaces of a certain structural type by studying maps between them that in a meaningful sense preserve the structure. So study measure spaces like this one, M, and you have a sigma on M and you have a mu on M. You have a sigma algebra on a set and you have a measure with respect to that. You could study maps that go from here to another set N that carries, of course, generically a different sigma algebra and a different measure. So study maps. Now, strictly speaking, a map doesn't map you from here to there. A map maps you, takes elements from the underlying set to the underlying set, but then you may employ the extra structure to impose a condition on the map. And that's what we're going to do here. As in topology, you have continuous maps that preserve the topology, well, by pullback. So you do here for measurable maps. It looks exactly like the definition for a continuous map, only that it employs the notions of measure spaces. So definition, a map F from a set N into a set M into a set N, because that's what a map is. But now we have M and N equipped with each a sigma algebra and a measure. A map F from N to N is called measurable. And you can't say this without saying with respect to mu m and mu n. No, that's not true. Okay. We're not quite there yet. I'm sorry. For the measurability, you do not need this structural element yet. For the measurability, you only need the measurable space, not the measure space. Okay, good. With respect to sigma m and sigma n, as much as a continuous map is with respect to the respective topologies. Okay, measurable if, well, for all measurable sets in the target, it is true that the pre-image of that measurable set with respect to the map F is a measurable set in the domain. Well, this is one-to-one the definition of continuous map, only with topology replaced by sigma algebra and continuous replaced by measurable. So that is a measurable map. Okay. Well, you immediately see that this is compatible with choosing a Borel sigma algebra that's made from open sets, right? And you would then immediately see that continuous maps are actually measurable. Continuous maps are not the only measurable maps, but they in particular are measurable. Now, okay, so this, by this general standard philosophy, it makes sense to define such structure-preserving maps between such structures. And maybe it's also meaningful to also call them measurable, because apparently everything is measurable, called measurable in this theory, okay? But it has a deeper reason, because these are the maps, if they go to the real numbers or the extended real numbers R bar, these are the maps with one minor extra condition beyond measurable. The measurable maps are the ones we can integrate, okay? So that's the meaning, because finally we want a theory of integration. And so far we measured sets. We can now measure here. Once we have a measure, we can measure sets on the domain. We could measure sets on the target. Anyway, we'll come to that. But just that you have the perspective, the measurable maps with minor additions, with a small minor addition of some finiteness, they will be the ones we will later on be able to integrate. Okay? Okay, so this is this, and we have the lemma to show that f is measurable with respect to the respective sigma algebras. It suffices to check whether, now it comes, it suffices to check whether for all sets A, you see, checking something for all sets in an unwieldy object like a sigma algebra is a hard task. But it suffices you check all the sets in a generating set of the algebra, where the algebra on N is given by this generating set. And now it comes in handy. So if you generate an algebra like this, then you only need to check for those in here, which is considerably less, if you're clever, than the whole set. You check there whether the pre-image of FA is again in sigma M. Okay, that suffices. You cannot at the same time check whether this is an element of a generating set of here, because the pre-image can be rather weird, okay? But it's actually from this lemma that you immediately see, if this is a Borel sigma algebra, then the generating set is the open sets, and then this is just the condition of a continuity, okay? So it means a continuous map in particular will be measurable. You know where the word corollary comes from? What that is? Well, in Rome you were invited to a dinner and you were the guest. You got a little woven thing of green plants, whatever, on your head, laurel crown or something like this, and that was the gift you got as a guest. And so the corollary is the gift you get from some theorem or some definition almost for free. Because, you have to entertain the host, but otherwise it's for free, okay? And so corollary is a simple conclusion.
Yeah, I have a small question with that lemma. Is that an equivalence? So does F measurable imply? Or is it just
no, it suffices to check, so that's the same condition. Whenever this is true, then this is true, and the other way around is obvious. So that from this follows is obvious because this is a subset from here, but the other way around is the statement. Sure. So that's it's measurable. It suffices. Yeah, well, it suffices exactly like sufficient condition, but the other direction is immediate. Okay. Good. Okay. So corollary. The first one is any continuous map is measurable with respect to the Borel sigma algebras. Why does this make sense? Well, in order to talk about a continuous map, you need a topology on the domain and the target. Once you have topologies, you have the Borel sigma algebras on the domain and the target. And so it makes sense a continuous map is measurable with respect to the Borel sigma algebras. It wouldn't make, without further explanation, it wouldn't make sense to say any continuous map is measurable with respect to another sigma algebra, because you need to link the continuity to the measurability, and that you do by the Borel sigma algebra. And the other statement is that any monotonous map, these are just examples, right? Any monotonous map, say F from R to R, right, is measurable. Well, that's more interesting because, I mean, it can be monotonous, but it could have many, many places where it jumps, where it's non-continuous, right? And, well, why is this? Proof. Why is this? Do you have an idea?
Open sets.
Yeah. Well, so the general hint is that the pre-image of an interval could be anything if it was any map, but for a monotonous map, the pre-image of an interval is an interval. And because open intervals, left half open, right half open, or closed intervals, because they're all measurable, right, with respect to the Lebesgue measure, not measure, nonsense, with respect to the Borel sigma algebra again. The measure doesn't come in. Because the pre-image of an interval is an interval, this follows. And so there are many more. So it's by no means are the continuous and the monotonous functions the only measurable functions, but there are two immediate examples. Okay, very important, and again, zero surprise to you if you remember the theorem on the composition of continuous maps for precisely the same reasons. Okay, the composition F after G from a set A to a set C of two measurable maps, F from B to C and G from A to B, is again measurable. And the proof, like the proof of some others, which I didn't point out in detail, proof is on the problem sheet. But it's no surprise. So the measurability is preserved under composition of maps. Okay? That's, of course, very useful. So mind you, I said that the measurable functions up to small extra condition will be the one, the measurable maps into R bar will be the ones that we can Lebesgue integrate. Those will be many more than can be Riemann integrated. Okay? And it's a very proper notion of integral. And I'll explain next time how precisely that works. And it's the notion I emphasize again, I said it before, it's the notion of integral we need in order to define the square integrable functions of quantum theory, right? Because the other set of square integrable functions or equivalence classes thereof, if you use the Riemann integral, it wouldn't be a Hilbert space. It wouldn't be complete, right? So there's no escaping this. But then again, you feel at home when next time I'll probably quote the theorem only, that any Riemann integrable function is also Lebesgue integrable. But the Lebesgue integral has this nice properties under exchanging limits and series and so on. So it's very nice. Okay. It's just it's a superior notion of integral for any practical purpose. So not only for physics, but also in mathematics, you use the Lebesgue integral because it just has the by far more clear definition and more powerful definition, but also much better, much nicer properties. Okay. So now I wrap up with two more small sections, so that section 5 is push forward of a measure. Now, as I said before, well, and as you know from experience, very often if you have a space equipped with a structure, and you have another space not quite equipped with that much structure, you may be able to inherit the structure from one space to the other space. Then in topology, you have, for instance, you have a topological space, you take a subset. Well, you can inherit a topology on the subset. It's a subset topology, okay? It's the intersection of all the open sets outside with that set. You need to show it's a topology again. You could also, in topology, say, how do I have to choose the topology on the domain if I know the topology on the target such that a specific function I want to be continuous is continuous? It's called the initial topology. The other way around, how do I have to choose the topology on the target if I have a topology on the domain such that a specific function, or even a collection of functions, is continuous? That's called the final topology. There are many, many constructions you can come up with. You always have to show that your construction then satisfies the conditions of the object you want to construct. And it's no different for measure spaces. There are many, many ways. You have a measure here, you want to induce it there, and you have to, there are many ways. You can go to the literature and see how you do this, and then there may be even several ways you inherit in a certain situation a measure or a topology and so on. And then it depends on what theorems you want to hold for the result. Okay, so it's a standard game. And I present just one way to inherit a measure, which we're going to use anyway, as an example. But don't think this is the only one. And it's a very natural way to inherit a measure if you're given a measurable map between two spaces. But it's by far not the only one. Okay, so take it more like an example in spirit, but one we're going to use. Okay, so let m, sigma m, and mu, well, let me write m sigma mu be a measure space. Measure, not measurable, that would only be this part, but a measure space. It carries, it's easy to remember because it's a measure space if it has a measure, okay? And otherwise, m sigma is only a measurable space. Let this be a measure space, and let n tau, nothing further, be a measurable space. So in a sense, the measurable space, there you know which sets could be fed into a measure, but you don't have the measure. You say, oh yeah, that's a set for which I could give a consistent notion of volume or measure. But I didn't prescribe which one. I know the sets. But whereas a measure space, you know the sets which can be assigned a volume or a measure. Volume is the more intuitive term. And you also know which volume which set has. Okay? So in a sense, this is the more politically correct one because this one says measure in liters, right, instead of gallons. Whereas here you know, oh yeah, we know these sets are measurable. They have a volume, but we're not saying whether we measure in liters or gallons. So I suppress any comments to gender theory. Okay. So, so assume you have this, and further, you assume that you have a measurable map. Let F going from n to n be a map, a measurable map. Let F from n to n be a measurable map. I could have also said let it be measurable. Then you have a measurable set, a measurable space, a measurable map. It's getting confusing, but you always have to have the right definition in mind. Further, let F to n be a measurable map. And so the idea is, well, F takes me from here to here. Could F take this one on its shoulders and carry it from here to here? Okay, could I push forward? So this is equipped with a sigma algebra and a measure. This is only be equipped with a sigma algebra, which I called tau. Well, I need to have this already being equipped with a sigma algebra because otherwise I couldn't talk about this being a measurable map, right? Because measurable map uses the sigma algebras, but not the measure. Now the question is, if I have a measurable map, can a measurable map carry this mu here, and I get a mu here induced from this mu and the specific measurable map? Yes. Then the so-called push forward, I think, so push forward is more like a term that's very generic, because this principle you have very often in differential geometry. Those of you who took my classical mechanics course, you can push forward vectors along smooth maps or differentiable maps and so on. You can pull back covectors, and here it's measures are pushed forward in this way along measurable maps, and this push forward is called F star mu. It's just a name, so this is one symbol, F star mu, is a measure on n tau, well, it better be, is a measure on n tau defined by, well, now you help me. So what do I need to do? So this F star mu, this new measure, is a measure on tau, so it needs to go from here to somewhere here, and it needs to take any measurable set A in this sigma algebra, and it needs to send it to a number like this, and the only ingredients you can throw into your meal is the measure mu that goes from sigma to there, and is the measurable map F that goes from M to N. Now you tell me how to define this. So this goes to F star mu eating A, needs to produce such a thing, and you now tell me how to define this with only these ingredients. Yes?
Mu of the pre-image of A.
Yeah. Mu of the pre-image of A under F. Oh, why can I feed the pre-image into the mu? So the mu lives on here, but it can only eat measurable sets. Why do you know that the pre-image of A, F is measurable?
The map is measurable.
Yeah, because the map is measurable. So that is why you need the measurable map, because otherwise you wouldn't be guaranteed that the pre-image of a measurable set in n tau is actually a measurable set in m sigma, right? It's the only thing you can write down, right, really, without further structure. So you could say it's a very natural construction. And obviously in this definition, there is implied a statement, a theorem, namely that this is indeed a measure. So this is a definition that you have to prove, and the proof is the problem sheet. Okay? So this is one way to inherit a measure, and it's one we're going to use. Okay. Now I wrap up by the definition of a set of measure 0 and the terminology almost everywhere. Which is probably something you heard before, but just for completeness. I still suppress the remark. Okay, so that's section 6. Sets of measure 0 and almost everywhere. So almost everywhere is a phrase that is applied in various circumstances, but it always, always, always has to do with sets of measure 0. Definition. Let M sigma mu be a measure space. A set with a collection of sets to which we can assign a volume and an actual assignment of a volume to all the elements in the sigma. Let this be a measure space, then a set A that is measurable, I'm sorry, in S, a sigma, a set A that is measurable is called a set of measure 0. Or maybe you can call it a null set. That's a little cleverer. Well, I guess it's shorter. A set of measure 0, null set, or German Nullmenge. Well, if, surprise, surprise, mu of A is 0. Okay, that's a set of measure 0. So it is a subset. Obviously, the empty set is a set of measure 0. But the whole point is there may be sets that are not the empty set and still have measure 0. Okay, so remark, there may be others, well, maybe other null sets. I call them null sets. I mean, the other thing is incredibly long to spell out. There are maybe other null sets than just the empty set, right? And the empty set is one is immediate from, well, it's not immediate, it's the definition of measure. It's the first axiom of the definition. And the whole point is there are sets that themselves are not the empty set, but have measure 0. What's special about them? Well, from the set theoretic perspective, nothing. From the measurable space perspective, something, because at least they are measurable. And from the measure space perspective, they're invisible. Okay, so seen through the glasses of the measure, they don't count. Okay, so they are the unwanted. No, they're not. Well, in a sense, they're also unwanted in some cases, and we mod them out, for instance, in the set of square integrable functions and so on. But anyway, it's an important notion, and many things we're going to prove in measure theory, and that will carry over to integrals and so on, is that many statements hold almost everywhere, and that's the final bit of terminology for today. Terminology. A condition, e.g. equality or convergence or ... whatever, okay, a condition is said to hold. Now it comes almost everywhere, and that is most common, is almost always abbreviated A dot E dot, almost everywhere, is said to hold almost everywhere if it holds for all M in the set in question. So there's always an underlying set M in our measure space. If it holds for all M in M without N, where without some N, no, it could be without some N with mu of N is 0. So that means a condition is said to hold almost everywhere if it holds for all elements of the underlying set M, except for some elements which, however, together must constitute a set of measure 0. Okay? then it holds almost everywhere. Okay? And so we have equality almost everywhere. And usually so let me write down 2 examples. I mean, it's really very simple. So let f from m to n and g from m to n be maps, and let m be equipped with a sigma algebra and a measure, but n can be any set, any naked set. Then we say f equals g. Of course, you could say f equals g if m was only a set as well. Well, that would not use the measure and the Borel sigma algebra. But if you now f equals e almost everywhere, so you write this qualifier under the equal sign, what we mean by this, by definition, is there exists some n in sigma. No, n is bad. There exists some a in sigma. I'm sorry for choosing n over there. There exists some a in sigma with mu of a equals 0, such that for all m in M without this 0 set, it's true that f of m equals g of m. And this is the equality that you can have on sets n. So this is the equality on n. Well, but that's just equality. I mean, I don't need to confuse you here, okay? So you see, in order to decide almost equal for 2 functions from m to n, you need a complete measure space as the domain. And similarly, you could ask if you have a sequence of maps m to n, and you have a map f from m to n. So there's an entire sequence of maps n in n. And M is a topological space and N is a topological space. Then you can, of course, decide on whether one... maps. Okay, maps is possible, but that's a little overdone. Let's take... I'm sorry. Let's take sequences in a set. Okay. No. Let me think. What do I want? No, I want. Okay. I want to define that one map converges against another map almost everywhere, but then a sequence of maps. I need a sequence of maps. I'm sorry. So you could talk about this converging against this, right? This would be convergence, and you know how it works. It needs to converge pointwise at every point of M. This needs to converge. Okay, so you say this converges by definition if and only if for all M in M, Fn of M converges against f of M. So this is now, because you fix the M, this is now a sequence in N, and you need a topology on N to talk about its convergence. So you need M to be a set, and if you just want standard convergence, and you need N to be a topological space so that you can decide on this convergence. But now we want to have the almost everywhere convergence pointwise, and then that's if you exclude a zero set. A in sigma such that mu of A is 0, but that's in M, so here you need a measure space in order to start talking about almost everywhere convergence pointwise. Okay, so I mean, yeah. Whatever you need, you get it this way, and whenever you see in almost everywhere, you have to think, okay, what are the objects, and where is it exactly, and what structure do I need where? Okay, and then you figure that out. And you work from the not almost everywhere notion, then you see it's this, you only need a set in the topological space, you go to the almost everywhere notion, you see where to take out a null set, set of measure 0, then you know, well, on that space you certainly need this space to be a measure space, okay? And that's it. And that will appear very often. Questions? See you tomorrow with the Lebesgue integral.